What specific problem does the new method or algorithm aim to solve in the context of interactive image editing, and why is this important?
The new method, FramePainter, aims to solve the problem of limited precision and flexibility in interactive image editing, which is often constrained by the ambiguity of language instructions and the lack of precise spatial control over image modifications. This is important because existing approaches typically require extensive training data and additional reference encoders to achieve plausible edits, which complicates the model architecture and increases computational costs. By reformulating interactive image editing as an image-to-video generation task, FramePainter leverages real-world dynamic priors from pre-trained video diffusion models, significantly reducing the data and computational requirements. Additionally, the introduction of matching attention enhances the model's ability to maintain fine-grained visual consistency and accurately align edited image tokens with their corresponding source image tokens. This advancement allows for more intuitive and effective image manipulation, ultimately improving the user experience in interactive editing scenarios.
How does the proposed FramePainter method work? Please illustrate step-by-step the process from input to output.
The proposed FramePainter method operates by reformulating interactive image editing as an image-to-video generation task. Initially, it takes a source image, which serves as the first frame, and an editing signal, such as a sketch, as inputs. The model, initialized with Stable Video Diffusion, SVD, processes these inputs through a lightweight sparse control encoder that injects the editing signal into the U-Net architecture, specifically targeting the features of the target image while preserving the source image's identity. To enhance the correspondence between the edited and source images, FramePainter employs a novel matching attention mechanism that extends spatial attention along the temporal axis, allowing for dense correspondence between image tokens. Finally, the output consists of a two-frame video that includes the reconstructed source image and the edited target image, effectively achieving flexible and precise image manipulation.
Can you provide a simple, illustrative example of how FramePainter operates using a hypothetical source image and editing signal?
FramePainter operates by reformulating interactive image editing as an image-to-video generation task. For instance, consider a hypothetical source image of a cat sitting on a mat. If a user provides an editing signal, such as a sketch indicating that the cat should be standing, FramePainter takes the source image as the first frame and the sketch as the editing signal. It then generates a two-frame video where the first frame is the original cat image, and the second frame depicts the edited version of the cat standing, utilizing real-world dynamic priors from pre-trained video diffusion models. The model employs matching attention to ensure that the features of the cat in the edited image correspond accurately to those in the source image, thus maintaining visual consistency and realism throughout the editing process.
What are the theoretical or practical benefits of using FramePainter compared to existing methods in terms of training costs and visual quality?
FramePainter offers significant theoretical and practical benefits over existing methods by reformulating interactive image editing as an image-to-video generation task, which allows it to leverage real-world dynamic priors from pre-trained video diffusion models. This approach reduces the need for extensive training samples, as FramePainter can achieve superior performance using only 1% or even 0.1% of the training data required by previous methods. In terms of visual quality, FramePainter excels in maintaining structural integrity and visual consistency, outperforming state-of-the-art approaches in both qualitative and quantitative evaluations. The introduction of matching attention enhances the accuracy of correspondence between edited and source images, leading to more realistic and plausible edits. Overall, FramePainter simplifies the model architecture and training process while delivering high-quality image editing results.
How is FramePainter validated or tested? Describe the datasets used, the metrics applied for evaluation, and the experimental setup to demonstrate its effectiveness.
FramePainter is validated through a comprehensive experimental setup that includes training and evaluation datasets constructed from high-quality videos. Specifically, the training dataset consists of approximately 20,000 image pairs, while the evaluation dataset includes around 200 samples. The evaluation metrics applied to assess FramePainter's performance are clip-FID, which measures semantic alignment, LPIPS, which evaluates perceptual similarity, and SSIM, which assesses structural similarity. The model is initialized with stable video diffusion and optimized over 20,000 iterations using the AtomW algorithm, with a batch size of 4 on 2 A6000 GPUs. The results demonstrate that FramePainter significantly outperforms state-of-the-art methods across all editing settings, achieving superior visual consistency, edit accuracy, and image quality, as confirmed by both quantitative metrics and user studies.
What limitations or drawbacks does the FramePainter method have, particularly in terms of applicability or resource usage?
The FramePainter method, while innovative, has certain limitations regarding its applicability and resource usage. Firstly, it relies on the availability of high-quality video data to construct training samples, which may not always be accessible for all editing scenarios, potentially limiting its applicability in diverse contexts. Additionally, although FramePainter reduces the need for extensive training data compared to existing methods, it still requires a significant amount of high-quality video pairs to achieve effective performance, which can be resource-intensive. Furthermore, the model's reliance on matching attention, while improving correspondence, may still struggle with very large movements or complex edits that exceed its designed capabilities, potentially affecting the quality of edits in such cases. Lastly, the computational requirements for training and inference, including the use of multiple GPUs and specific optimization techniques, may pose challenges for users with limited resources.